We have everyone back. Okay.
Good.
Yay! Hey, it's always good when things work. All right, hello everyone. Welcome to this week's Learning Space. My name is Nicole Gugliucci. I am a postdoc with CosmoQuest. I have with me my co-host here, Georgia Bracey.
Hi, everybody.
Literally through this wall.
No, so close. Yes.
So close, so close.
I know.
Oh, we're neighbors. And I also have Tom Field, who's going to be talking to us about spectroscopy.
Hello.
Hi, Tom.
Good to see you.
Welcome. So we have a couple of things to go over. First of all, if you would like to say hello and ask a question and chat with us, which Guido is already asking which one to use. We prefer the Q&A app, so I see Guido says hi on the Q&A app, Nancy says hi on the Q&A app. Hello, everyone. I know some people still prefer the event pages, either the normal one or the video one. I will try and keep up with those as well, but the Q&A app is the best bet. And I'll try and watch the YouTube comments as well. So feel free to join in, use the Q&A app, say hello, +1 to each other's comments, and do all that fun stuff. So we want this to be interactive. We also have a hi from Tom. Yay, hi. Awesome. Okay, so I do not have a hands-on demo to show today because I'm still in post-science online stuff. I was gone last week. Georgia hosted the show, and I bumped in 20 minutes late. So thank you.
You were there.
I was there. So I still need to go back and catch the beginning of that show because it seems like it was a really good conversation. So that is all good stuff. So I don't have a demo but we are going to be talking about some interesting stuff you can do in the classroom or with groups. And so Tom, tell us a little bit about, so I'm going to share the link while you tell us a little bit about RSpec Astro, your introduction to real-time spectroscopy.
Yeah, I was an amateur astronomer for years, and I wanted to do a little science. I think we all have inner scientists in us that are looking to get out. You actually have outer scientists, but whether it's a teacher who isn't specializing in astronomy or an amateur, or we all want to do some science, and there just didn't seem to be much that was being done except imaging. And so I picked up a very small grating that screwed into my telescope, and was just really astonished by the science that I could do. And so I ended up writing a piece of software. My day job pays the bills, but the software is where the fun is. And basically, what I enjoy is introducing, whether it's educators or amateurs, to the possibilities that with very little equipment. I mean, I think most of us think we need to have PhDs like most of you, as well as big telescopes like many of you, I suppose, right, to do spectroscopy and actually discover science and discover that we can observe physical properties of stars at a distance. So that's how I got involved in this, and it's been very exciting to be, I feel like I'm an ambassador or an evangelist for amateur or low-resolution, inexpensive spectroscopy.
So spectroscopy is incredibly important to all of astronomy because light is still the way in which we get most of our information about the cosmos and breaking down the light and seeing what it's made of. So this system, so when you say low resolution, what does that mean, low resolution? Low spatial resolution, low spectral resolution?
Yeah, low spectral. I mean, amateurs can get very high-end equipment, but with a simple grating like this, and this is just an 1.25" grating that sells for less than a couple $100. Just screwing it onto any old camera. And we could talk about classroom lab tools, but this one is really where we do the astronomy.
Yeah.
We can get down to, and again, amateurs talk in angstroms, and we're talking 30 angstrom resolution. So you can see all sorts of features. Again, just a review for people who aren't familiar with it, of course, what we're looking at are the absorption, for example, of the gases around a star that's basically cutting out certain portions of the spectrum. So we see gaps in the otherwise Roy G. Biv continuous spectrum. And we can actually observe at a distance, the composition and other physical properties of stars, as you all know.
I can show the very detailed, I think, is that a Nichelle spectrum?
Yeah, it is, and that's the sun.
Yeah,
and you can see those gaps, and each of those gaps, of course, is related to a particular electron jump in the actual atmosphere of the sun. And in fact, I think the next, let's see, where are you in the slide deck?
That's number one.
Oh yeah, just go. Yeah, go one more slide.
Okay.
We can zoom in a little bit.
Yeah.
There we can see again just certain gaps. In one more slide, we can actually see them named, where we can see that again the absorption that's due to transitions of electrons in the shells or in the shell of the sun of magnesium are creating those particular absorption features on the bottom, or on the top, excuse me. So to be able to see these and observe them in a telescope makes it real. Otherwise, it's just a, paper theoretical experience that students and amateurs are getting. And so with this grading, really, if you just use it visually, you see a little rainbow, but you can't really see the gaps in the spectrum.
Right.
For that, you need software that actually blows it up and then graphs it. And that's what I ended up doing, was writing a piece of software to do that so that we can do it real time under the stars, with video even. And I'll set a telescope up in a high school parking lot, like a 6-inch telescope and a video camera, and show people the absorption features on, for example, Vega, a bright star, for example.
Mm-hmm.
And it's amazing what we can see. I'm just looking for an example in our slide deck here. Try slide 56. See if that shows.
That is showing the Wolf-Rayet star.
56 is? Wrong. I've got my numbering wrong. That's the Wolf-Rayet? Okay, well, let's look at that. That's a good one. That's fine.
Yeah. Oh, wow.
So this is, look at, and go one more slide ahead if you would.
Oh,
So
okay, here we go.
So at the bottom we can see the rainbow, and you can see Janet here in the UK with just a 30-second exposure and a DSLR and a grating. So in terms of hardware, all she had to do was pick up a grating. She's seeing very, very bright features on this star, emission lines.
Mm-hmm.
Now, frankly, you all know a lot more about these particular types of stars than I do. I had to go to Wikipedia and read up on Wolf-Rayet stars.
Right.
But these are stars where, as I understand it, and you, I hope, will correct me when I get it wrong, the outer shell of these late-stage stars has been blown away.
Mm-hmm.
So those peaks that we're seeing there are basically soot, glowing carbon. So we're looking down into the shell of the star, seeing that feature, that emission line of glowing carbon. And that, for a student to see that and to have a graph of that like we have that the software just produces, it's a home run. I mean, they're doing astrophysics. They're actually observing features on a distant body. It's amazing. Really, it's amazing.
What I love about this picture is it's showing you the squiggly line problem that sometimes we have with astronomy communication, because spectra are fascinating. And when you're used to looking at spectrum after spectrum, you see this squiggly line graph and you think, oh, that's really exciting, look at the emission peak and look at the wings, and you can get really excited about it, and you show this or put this in an article meant for public consumption, and people are like, that's boring. That's what's happening. And I like that you take the rainbow down here, because people are familiar with seeing that rainbow from a prism, for example. Then they can extrapolate, okay, there's absorption and emission, and then you just flip it on its side, you graph it, and that's where you get the squiggly line graphs that we get so excited about. So I like that representation.
Did you say wings, Nicole?
Yes, I did say wings.
Explain wings.
I'm trying to show you with my hands, and that's a terrible thing because my webcam's not on.
I can't see it.
How wide it is, the base.
Okay, yeah.
If there's faster moving material that creates a wider base, that could be the wings of the line. So yeah, everything about that line shape is really important to spectroscopists, but it's not, nobody ever lines them up like that and says this is the rainbow and this is what it looks like when we graph it.
Yeah, that's a great connection to make. So
see if slide 51 comes up for you.
Sure.
That's a really colorful one.
Oops. Yeah, screen share. Yay. Watch, this will be the day it breaks on me. Is this it?
I'm not seeing anything.
There's something.
Can you see it, Georgia?
Yes.
No, that's a good slide actually to look at. We'll go back one after that.
Okay.
So this is just to familiarize people with the way this is happening, and that is you can see at the bottom we've got a star, and then we inserted in the light path just this simple grating that you see in the middle there. And
Can you hold that up again? Sorry, I had it. Yeah.
Thanks. So this is the grating that we can screw that with a DSLR. Like if you have just a DSLR lens like this, you can screw a little a thread adapter on like this, and then the grating. And that's all there is to it. In fact, on bright stars, you don't even need tracking. If you get the grating oriented right, then you can just do a 30-second exposure and get a spectrum without any tracking at all. So there's no additional equipment or a complicated setup. But
So
now go back. Go ahead. There.
Is this using just the camera, or is this attached to a telescope? Like how large of a
This
telescope?
is just, well, this particular one is a video camera attached to a telescope.
Oh, okay.
So this could be a live spectrum. In fact, go back to that really colorful one, because that's a good example of some of the elementary astrophysics we can do.
Is this the one here?
Yeah, that's a cool one. Each of those is a separate image. And it says at the bottom there, for people who are into all the hardware, it's just an 8-inch telescope with a video camera. And so each of those strips is the rainbow of a different star that's at a different temperature.
Right.
And so you can see differences. The hot stars are at the top, and then down at the bottom are the cool stars. And you can see that the different temperature stars have different gaps in that red, orange, yellow, green, blue, indigo, violet rainbow.
Mm-hmm. Mm-hmm. And historically, you can show that the hydrogen lines are strongest at A, because that was how they were first set up alphabetically, with A being the strongest lines. A, B, C, D, E, F, G. They went down the alphabet, then they decided we don't need that many letters, and that's how you get O, B, A, F, G. I have to say the words. O, be a fine guy, kiss me. O, be a fine girl, kiss me.
Listen, there's a much more politically correct expression.
What is it?
But I don't know what it is.
Oh. Well, guy and girl are interchangeable.
There's something about grades in there that's gender neutral.
Yes, I think you're right. But anyway, you can talk about the history of the classifications by showing that it's strongest at A, and works its way down.
So whether it's looking at the temperature of stars or where's that other? Oh, there's that Wolf-Rayet star. There's another slide. I don't know what's happened to our numbering. 60 here. See where you get on 60. It should be M57, a couple rings, or what's it?
Nope, I get the Orion Nebula. Oh wait, I see it. I found M57.
Well, that's...
No, because I think the picture is cool. Yeah.
Yeah, that is neat. So on the left we have the object that we'd see if we just look through a telescope, and it's the Ring Nebula. It's a gas sphere around a central star. And then when we put it through the grating, we can see very clearly just two really bright colors. That's the component colors. And maybe you guys want to talk about what those colors indicate.
Sure. So if any of you who are familiar with the Virtual Star Party know that a couple of our astronomers film particularly, use filters that allow them to see just the H-alpha. So in this case, they're just seeing the emission from the hydrogen atoms. And then occasionally, I think Gary uses oxygen as well. A couple of the other guys use oxygen filters as well, because as you can see right here, these nebula, these objects that you're looking at, glow brightly in those particular colors. They do that so that they can filter out all the light pollution from human sources, but then they zero in on these particular parts of the spectrum.
Yeah, so what I've found over the last several years, and as I said, I've really been a proponent for this in education, is that at the high school level, and typically it's going to be an instructor, a teacher who's got an interest in astronomy, will do this kind of project with a handful of students or maybe a class, and what they'll do is go out and just with a simple camera or a video camera and capture some spectra, just to make the study, the topic, more real. So there's something about, whether it's as an educator or whether it's as an amateur, what my experience has been is when I get the data in my hands, and you guys have seen it too, when you get the data in your hands, all of a sudden it becomes much more real, things are remembered more easily, and it becomes significant. Otherwise it's just theoretical.
Right. We have a couple of questions and comments. Tom Nathies says the charts are a little small. I think I keep forgetting to click on to make it embiggen, so hopefully I'm embiggening them now. Yell at me again in the Q&A app if you can't see the images. I should be sharing them properly now. And Nancy points out that nothing is less politically correct than the mnemonic used for resistor color codes. Insert joke about engineers. I added that. She did not say that. But she also asked, Tom, are you a programmer by trade?
Yes, I am a programmer by trade, and so this was a hobby project.
Mm-hmm.
I mean, what happened, like a lot of us, I think, is I tried using the freeware that was out there, and it was just too complicated. And you, as professionals, know that some of the tools that you work with, IRAF and so forth, they're way overpowered for what we mere mortals need.
And also sometimes really terrible. I mean, let's be honest.
You're my host. But
let's be honest.
Well, the amazing thing about them, as you know, is they have such an accumulated body of knowledge and testing and proven ability. Nobody wants to risk something new, and I don't blame you.
Yeah.
So, but for what amateurs or educators need, again, the idea is the software will be easy to use, and I've been really delighted to have an opportunity to do that in the field. It has to really be plug and play. You know, maybe later we'll talk a little bit about the classroom lab bench spectrometer that doesn't take going outside. But as we were going through focus groups with teachers, one of the things we heard, which I think pretty much captured it all, is one of the teachers said, you see that button labeled calibrate on your screen? That has to go away, because a teacher does, when they see the word calibrate, and I understand completely, the last thing somebody with a room full of students wants to be doing is calibrating a device. They want it to just work. And it's great if calibration's available, but it's not something you want to be doing in front of a large group of people. So yeah, I wrote the software, and am continually fighting the battle that most software developers have between adding complexity and keeping the user interface simple. And of course, there's lots of examples where people have done very well at that. But the minimalist approach, I mean, even just tonight, starting the Google Hangout, I re-experienced the discomfort of not knowing where to go, you know. And it's good. It's always good for all of us to remember how awful that is as programmers, so that we do a good job of eliminating that need.
It really is, and I'm glad to hear, you know, you did some focus groups with teachers, and we've done a lot of that here too. And it's easy when you're immersed in anything, whether it be your, you know, your software, your device, your set of curriculum, you know, your activity. It's so comfortable and normal to you, and you forget that you just need to sort of step outside that. And not that somebody is less intelligent or doesn't have any expertise or anything, it's just, it's new to them, and there is that discomfort, and it's really good to, you know, give people time to get over that, and to get comfortable. So, you know, focus groups are great. You know, it lets you get ideas that maybe just didn't occur to you because you're so comfortable, you know, with your product. So what else did you hear from teachers in your focus groups? Be interested to hear.
Not a lot, you know. No
calibration, right?
Nobody likes manuals.
Nobody likes manuals.
Not only teachers. None of us read anymore. I mean, really, we don't
want to read, right? Don't have time for that, right?
I read fiction. That's about it.
And some software manuals I've read I thought was fiction when I compared. So one of the things that I do in my day job, which I've put into this product that I'm really excited about, is video tutorials. You know, it's an on-screen tutorial, so it's like somebody just sitting by your side saying, "Here, let me show you how to do that." And as long as they're short, then they're tolerable. The disadvantage of videos is they're not random access. When you want to look something up, you don't have a book to flip through. You can't read it while you're watching American Idol or whatever you're watching.
Right.
Yeah, an index, table of contents, all of that.
Yeah.
So, I mean, and what I found is that students, we had our classroom unit set up in a middle school last month over near Microsoft, so the kids were particularly well schooled. And kids, it's amazing. There's this, and I don't know, do you guys know this term CSI effect? Have you heard that term in work?
No.
Having to do with the show CSI? Like everybody thinks that the
data.
Yeah. Oh, yeah, like, let me clean up the image.
Yeah, right. When they zoom in on the license plate, 6,000.
Yeah.
But no, the CSI effect is that unlike 10 years ago, students are much more comfortable with technology and with the CSI-like forensic equipment, and it's no longer as nerdy as it used to be. And so students, and also because everybody's on phones and computers, it's not nearly as hard for a student to sit down at a new application and figure it out. They're scary fast at doing that. and self-teaching. If they're motivated, they'll just figure it out. And of course, the other thing we're hearing a lot of is how to encourage teamwork. We're working with a large university now that has 2,000 Astro 101 students per year come through their their lectures, basically. And so they're looking for a way to not only do a little science with the students, but grow teams. I mean, they're not going to learn a lot of science in a 101 class. It's too big a class. There's too little time. Although I don't mean to offend anybody by saying that. But the growing of the team, and so one of the things we're emphasizing in this curriculum, like any lab work in the school, is how you create teams and how the teams work together and all of those collaborative things, which is so important in the work world today.
Yeah.
So I think that's pretty much what I heard from teachers, except I love showing them this grading foil and have them cringe at just how frustrating it can be in the classroom.
Yeah, why don't we talk about the teacher system and how this grew into being a resource for teachers?
Sure. I mean, what happened is I live in Seattle, so we have a particular disease here called Bill Gates-itis. We have dollar signs in our eyes. I thought, hey, maybe I can make some money on this. And it's hard to do. It's a niche market. But we went to the NSTA show about 4 years ago in San Francisco. Maybe some of you were there. And just with the software and a do-it-yourself camera that we put together, not really knowing what to expect. And teacher said, that's really cool. We like that with a gas. A lot of us have gas tubes like these. Just fell off the desk.
Woohoo!
They were gas.
How sturdy is it?
Yeah, now they're basically shards of glass.
Oh,
but
no.
a gas tube device like this, or this is a particularly cool one that I like. It's an LED column.
Oh, that's cool.
All the colors of light, and you can see some really neat things.
Oh, I love that. I saw that on your website, actually. The brief moment I got to look at it today. That's really cool.
It is really neat because what you can see is that each color disperses differently. I'm not sure we have a slide for that or not. But so the teacher said, yeah, slide 122.
Woo!
Next, it's the third from the last.
I think I see it. Oh, what? Is that it?
It's a screen with a red peak on the right.
Yeah. I can have screen share. Yay.
Yeah, that's it.
There
And
it is.
that's that big N or whatever.
Oh.
So there's the. Oh, we lost it.
I'm still here. There we go.
Oh, there we go. So on the left, that's a live video view, whether it's in the classroom or under the sky with a telescope, and you can see the vertical column there on the left of the LED. That's right. And then right there where you're pointing, Nicole, you can see each color is dispersed a different distance.
Yeah.
So even though at the top you can see a white light with the full rainbow, and so the students go, oh yeah, I know, the rainbow is all the colors. I mean, that's easy for us to teach and to be parroted back. But when we throw a change ball and show one color at a time down below there, it helps the student understand that we really are talking about separate colors dispersed because of the rainbow-like prism, the grating, dispersing the light differently. And then over on the right, we've graphed that intensity. So now not only are we showing them on the left the qualitative, but on the right we can see the peak at 0 there. Let's start with the 1, 0 there, Nicole. Thank you.
Yeah.
That 0 peak is the light on the left, the column itself. That's just an intensity. And then on the right is that red peak, which is showing us again where that I'm not saying this very well. The red arrow on the left is where that peak came from. See that red arrow?
Right.
Okay.
Yeah, that. So what we're doing now, I'm seeing Georgia again. So what we're doing with this screen
it's okay. The audience can see what I select, but you can't
great.
see what I select. It's very odd.
So what we're doing is on the left showing them qualitatively the way different colors get bent with a spectrometer. On the right, showing them quantitatively how that graph relates to it. And that really puts things together for the student. So the LED column is really an effective way to demonstrate the different colors in spectroscopy being dispersed different distances.
Do you do this with an incandescent bulb that you make hotter?
I don't today. That's just, I've done that, but you can do it. In fact, I've got the little, rheostat and bulb here to do that.
Yeah, because we do that in class. We show the filament. The filaments get, to show Wien's law, you show the filament getting, colder, hotter, colder in color temperature, warmer in whatever, red to orange to yellow to white. But you don't see the spectrum of it, but you'd actually see that hump evolve.
Yeah.
And that's black body radiation right there.
Yeah, well, the software has the Planck curves built into it so that you can compare.
Okay.
But we haven't done everything that needs to be done to make that happen.
Okay.
So whether it's looking at a LED array or the other thing is just a hydrogen gas tube, like I was showing before, which has such very distinct features. And that one of the things that teachers do is they'll do a lab where the students have to identify a mystery gas tube. Try slide 20.
Oh my gosh, I've done this lab. Oh my God.
Yeah, but you may have done it with a yardstick or a meter stick or.
There was a little thing on a track with the angles, and oh my God.
Yeah. It sounds like it was a winner for you.
When they give you argon, and you just cry because there's so many lines. Hydrogen's easy.
So there on the left, you can see the gas tube.
Right.
Good. Yeah, there's the gas tube on the left, and you can see the spectrum on the right, or just to the right of it, an inch right there. That's what the students have so much trouble finding with these rainbow glasses. They just can't, because the angles have to be just right for their eye.
Yeah.
And then over on the right, we can see some very clear peaks.
Right.
Those peaks are the fingerprint for hydrogen or helium or whatever the gas is we're looking at.
Well, there's definitely hydrogen that's had some other things mixed into it. You can tell when the tubes are old.
That's right, absolutely.
They're not clean anymore.
Yeah. So whether it's that in the classroom, just to jump around a little bit, go to the very last slide. You might even be able to hit the N key. I don't know.
Whee! I don't know how
this is Comet ISON earlier this year or last fall. And this was done by a man in India with just a DSLR and an 80mm refractor. It could have even been a zoom lens.
Look at all the green. Wow.
Yeah.
Yeah. Well, on the left, we can see the very leftmost thing is and this is just for the DSLR. Wow. On the very left is the comet itself. You can see we're calling it out there with the comet. And then just an inch or two to the right is the spectrum that looks like a string of jewels. It's very pretty. Yeah. That's one of the things that's fun about this is it has a certain engagement just because the colors aren't boring. It's not mono. Whatever it takes to get people engaged.
It's kind of artistic, yes.
Yeah, it is. Then so over on the right, then we've graphed those color intensities.
Wow.
And those peaks are basically mostly glowing carbon.
I've got my head tilted to try and read the letters. It looks like carbon, C2.
Yeah.
Cool.
So this now, unfortunately, we can't really schedule comets or interesting objects, as you researchers are frustrated by, I'm sure.
Yes, and Fraser Cain. He wants another comet. If he has his way, there'll be another comet.
He wants to name one, right?
Oh, goodness. Yeah, that's spectacular.
Yeah, it's pretty exciting to do because it gives the students a chance to actually print a graph out, have the results. In the software they can save it as a bitmap or an XY plot and pull it into Excel or whatever they want. Yeah. So it gets pretty exciting. The students really get engaged. It's surprising. Now, for people who do astronomy already, there's all sorts of exciting things that they can do. Simple things. For example, try slide 104.
So, Tom, do you have like a booklet of activities or suggested things to do?
On the website, we have a
with all this
sample results page, which shows. These are mostly astronomical projects, the kinds of things, and most of the slides I'm showing here are on that page. So this, I don't know if you can see that PowerPoint slide. There we go. This was done with a modified security camera, so you can do this like.
No.
Oh yeah, yeah. See, I love showing you professionals this stuff because you go, no, I can't be.
No, that's so cool.
It's less than 15 minutes of integration time.
Mm-hmm.
And those peaks, again, I've got a picture of what's his name over on the right, Martin Schmidt.
Martin, yeah.
He was in his mid-20s.
Wow.
And stared at those peaks and went, well, I don't know what they are, but let's just prove they're not hydrogen. And lo and behold, they were.
Yeah. Yeah. So this case, the audience isn't familiar. 3C273 is a very famous quasar. It was the first one for which they figured out that the redshift put it way outside of our galaxy. And this is also the first quasar I did research on when I was a little baby radio astronomer. But it was a big deal that it was found to be, the spectrum was so far redshifted, it was so far away, it was this cosmological object. That was a big deal. And so it's really cool that they did this data with a security camera. That just blows my mind.
Yeah, just a small 8-inch or 6-inch scope.
Yeah, because that is one of the brightest quasars in the sky. You can see this one.
Yeah, or look, try a slide. Just one more techie example. Slide 93. That's 93.
It's for me.
Huh, that's weird. We'll go up a couple more if you would, please.
Okay.
There, that's good. So if we look, this happens to be supernova 2011. And again, these aren't schedulable, unfortunately.
Yeah.
But the very bright ones amateurs can look at. And on the bottom, we have a spectrum done just with a 9-inch telescope, and you can see at the bottom less than 15 minutes of integration time.
Mm-hmm.
And there's a very deep dip there that helps us identify this as a particular type of supernova. Now, again, it gets pretty techy, but the interesting thing is with just some simple math that's on the top there, you can calculate how fast the shell of that supernova is coming towards us.
Wow.
So now you're engaging students. Everybody loves supernovas. They're big. They make, big, they don't make a lot of noise, perhaps.
They make boom, in metaphorically.
Thank you.
I can imagine.
And to be able to calculate with a backyard telescope the speed that shell is coming towards us because of the Doppler shift. And it's not a lot of math. Even a knuckle-dragging programmer like me can plug a few numbers into a formula I pulled off of Wikipedia, and actually detect movement at a distance, at an enormous distance.
Yeah.
So, again, just the kinds of projects that can happen.
So do you know of anyone that has done that with the recent one in M82?
Yeah, they have, and I had hoped to have that slide. I mean, I thought I'd sent you the PowerPoint show that had that, but I didn't.
Okay.
I'm going to try and bring it up because there's a particularly interesting view of that, because over time that speed drops, and so amateurs have taken spectra by the day for a couple of weeks, and you can actually see that dip moving to a slower and slower expansion rate, which is, again, really amazing. Yeah, this most recent supernova, I think that the telescope manufacturers for amateurs and for educators just love these supernovas because everybody gets all excited about astronomy again. Comets, supernovas, it's been a good year. For
when things blow up, we like it.
Yeah, exactly. Yep.
Nothing wrong with that. Well, mostly nothing wrong with that.
Makes a lot of light,
As long as they're, the supernova aren't too close.
Oh, here, try slide 111 just to show the teachers what they can do with the DSLR. It'll be a little different than that. I'll try and walk you to the.
What does it show? Because my 111.
It's a camera in the lower left corner, a DSLR on a tripod.
I think I'm like one off.
Yeah, I probably deleted a slide after I said it.
Extra slide.
Yeah, because I'm like, is this it?
Yeah, that's it.
Okay.
What I wanted to show on that, it doesn't show up very well here, but is, let's try one other different slide. That would be, give me one moment here to find it.
Trying to make it a little bigger for you guys. I've got rid of the toolbars.
Slide 41-ish. That's one back.
There we go.
Please, thanks. So there's an example of how to do spectroscopy with a grating and just a DSLR. It's just sitting on a tripod. There's no tracking. There's a little grating on the front of the zoom lens.
Right there.
And I mean, it's not something you just point and shoot. You got to get it pointed right to the star and get the focus right. There's a little bit of technique involved, but it's something that students can easily do. And then at the bottom, we can see the actual spectrum. We can see some gaps in that rainbow that are the result of the absorption that's going on this particular star, which is Vega.
Yeah, so those are the hydrogen lines because Vega is an A star. Cool.
Yep.
I remember on your website you recommended Vega as a star to maybe try first. So is it the brighter, the hotter stars better, obviously?
With a DSLR, and we don't have big aperture as amateurs or as educators usually compared to what you all professionals have. So Vega is particularly bright, and the other thing is, as Nicole mentioned, of course, it's a particular type of star, a type A star, that has very strong, as you know, very strong absorption lines, so they're easy to spot. Some other stars, the lines are more subtle or not as broad or shorter, so they're harder to see. But again, it's been fun. Even I was at the AAS. I had a booth at the AAS last year, and to show top researchers, as I elicited from you guys a few minutes ago, showing you that quasar, to show how easy it is to do something with just amateur-grade equipment. This is, of course, what we're doing here. Professionals 100 years ago would have given their left leg to be able to do it.
That's right.
Yeah, but when I was an undergrad, I would have given my left leg to be able to do it. I'd still give my left leg to be able to do it just that simply. Like, oh my gosh, that's really cool. I have to ask if KISS stands for Keep It Simple, Keep It Stupid?
Keep it simple. Yeah, I should get rid of the second S, I think.
Because Tom Nathy included that in a comment a little while ago. He says it's the KISS principle. Keep it simple. Oh no, keep it simple, stupid.
Yeah. Don't keep it stupid.
That actually came up as a comment a while ago, so I just had to point that out. Thanks, Tom.
Words to live by.
Words to live by.
Another interesting example. Try 63-ish.
Alberio.
Yeah. So again, this is a showpiece. Again, for anybody who's out with a telescope, because the colors are so pretty.
Yeah.
You can see it there in the right in the cutout, the black, that's the gold and the blue, the different colors.
It's gorgeous.
It actually looks like that to your eye. It's one of the few things you can show people at a public night with a small. Yeah, we have an 8-inch telescope for our public nights. This is like one thing that has color.
Right.
Yeah.
It really does. It's especially if you defocus it a little bit, it gets a little bigger and a little easier to see. But when we graph those colors, those two stars, we can see a lot of on the left there, as Nicole's showing, a lot of the light is over in the blue for the one star,
right? And
for the yellow star, the light is not as leftmost.
Yeah, but that's that black body spectrum again that you want to be able to show, because that's so important in physics.
So now we're measuring the temperature of stars with a backyard telescope.
So cool.
So there's lots of things. Again, getting out with a telescope is a big investment in terms of time and getting the students in the evening and getting the telescope set up. And so I think that's for really the diehards. Unfortunately, I mean, I don't mean to undersell it and discourage people, because I think it is a fascinatingly exciting for the students to do that, especially even looking at the blue gold star like we were just looking at, the double. But doing something in the classroom with gas tubes is more likely to be easily done. Doesn't require kids to come in at night. And so with this is the spectrometer. You may have seen a picture of it. In fact, there's a slide. It's the next to last slide.
Oh, yep.
Thanks for driving the slides, Nicole.
Sure. There we go. This one?
Well, that's an interesting one. That's not the one I was thinking of, but we can look at that for a second.
Sure.
There's a gas tube in the lower left, that violet tube.
Yeah.
And this happens to be in a dome, but it could as well be in a classroom with just a standard overhead. So here the whole class is seeing the spectrum together. Yeah,
there it is up on the screen.
And that's 123?
That's 123 for me. It's even, look, it's even there.
Go one more.
I'm not making it up.
There, that's what I wanted to show you.
Okay, that's the camera.
Typically on your lab bench in the front of the classroom, that's what you have. And we've seen most of those pieces. On the left is the gas tube power supply that is often sitting in a closet dusty, we found. And then next
Yep.
And then next over is the LED array, which just is fascinating because the colors are just so bright and pretty. And there's nothing wrong with pretty. And then on the right you can see the camera. And so just pointing the camera at the gas tube and then projecting the software screen on an overhead allows everybody to see what you're doing if you're not doing it. Oh, there you go.
So we don't want to use these anymore?
I still think they're enough fun to use.
Oh, they're just
good. They look good. Yes.
Yeah, we're styling. We need to get George a pair.
I know. I'm like out of it.
No, if we're going to be styling, then we have to go the full.
Oh God! I can't match that.
Come on, Nicole, don't look away.
I can't match that.
No. See, this is the hydrogen absorption lines, right? That one. That. Now Now, I think this might be a first for your Cosmo Quest.
Yes, yes,
Wow.
awesome wigs. We need more
Wow.
awesome wigs.
My wife says dress for success, you
There
know?
you
You just have to go.
Just for the job you want.
That's right. Pushing a broom behind the elephants, I think, is what this gets me.
Oh, man.
Well, Nicole, you got to get one of those. That's all there is to it.
Don't encourage me. Don't encourage me. But this is, I mean, yes, these are the ones that I use to entertain 5-year-olds, but and myself. But, you know, they typically give the student the little tiny, you know, diffraction grating. Maybe I could put it up to the camera.
Oh, wait, yeah, hold it closer. I think I can see.
Yeah, they give you this diffraction
Yeah,
grating.
That actually works.
To look at the tube in the classroom. So I've seen it in the front of the classroom, students, you know, trying to figure out where the spectrum is. You can kind of see something.
Actually
reflecting.
looks
There's a
pretty
red
good.
one
Hold
here,
it
just to the right of your right ear.
What's it reflecting? What is that?
I don't know, but
Oh, that's my phone.
your
Okay.
phone. Yes.
That's my desk phone. It's a
Right
reflection of my
behind
desk
you.
phone.
That's a
I forget I have an office phone.
I like it.
This analog equipment. All
Yeah.
right, I'm gonna wear these for the rest of the show.
Now, I remember being in a lab, I don't even know if it was high school or college, but using the little diffraction gratings and not being able to see anything, and because I was just looking straight forward through it, and you know, you have to look like out to the side, which somehow I missed that piece of crucial information, and so, and a lot of other people around me missed it too, so I didn't feel too bad. But you know, once you did that, yes, you could see it, but it was about 5 minutes of sheer frustration. So, you know,
Chaotic.
which is sometimes good, but usually to be avoided.
Right, right.
So, you know, and as we're seeing more and more interdisciplinary studies where we're trying to, you know, combine different topics, try slide 12. See if we can see that, Nicole.
Ooh.
I did off by 1. I'm not sure I added or subtracted in the right direction. We'll see.
Sensitivity of the human eye?
No, go one more.
Nope.
There's a little picture in the upper left of a fossil. Yeah.
Fossil. Where am I going to fossil? Oh, here we go. All right, let me pull that up. Okay, this one?
Yeah. This is a 500 million year old fossil. And a guy, Professor Parker, yeah, go to the next slide. A guy named Professor Parker in the UK looked at that and he said, you know, that looks like the fine lines in a diffraction grating in a spectrometer. And he said that looks like maybe this critter had some colors. And so on the next slide we can see his guess, you know, pure guess as to what this particular critter may have looked like.
Yeah.
But at this particular time in planetary life history, since humans only go back 4,000 years, we know that this doesn't cover them. But the explosion of diversity that happened in this particular era may have been as a result of the evolution of, I mean, it doesn't make sense to be visually diverse as animals unless you can also have animals that are seeing that diversity. So eyes and appearance co-evolve together. So that's just, again, an example of some of the natural history that we can look at in terms of, you know, fossils and so forth.
Cool. We have a question from Tom. For solar spectra, I don't know if you've done solar spectra with this, can you see magnetic shifting with sunspots or solar rotation? Can you actually see line splitting or anything like that?
No, not with inexpensive equipment like this. This takes higher-end equipment with more resolution than that. There is a slide, it's 5 from the end. Try 121. An example of how we can do solar spectra.
The sewing needle?
Yeah.
Okay, cool.
Because the thing about this particular grating is that it doesn't have a slit. That's why it's so inexpensive. Right. Professionals have a lot of lenses and a slit so they can look at extended objects, and we don't with the inexpensive equipment like this. But if you stand up a sewing needle, and you can picture me in the sewing shop about 3 years ago with an armful, I wanted to make sure I got the most reflective, purest sewing needles, and so I had like a stack of about 20 different packages, and I was getting lots of, shall we say, interesting looks from the clerks as to, you know, what's this guy doing? Why is he buying so many sewing machine needles? So, but once you set the sewing machine needle up vertically like that, you can just look at the reflection, and you can see some of the features, some of the Fraunhofer lines, very broad features. It's a very, very coarse spectroscopy, but it's enough to be able to see some of the features.
Very cool. You're supposed to say something like, "It's okay, I'm doing science," or Okay, I'm a scientist.
That's how you get away with your weird
Makes them feel
purchases.
better.
And I'm buying 18 pounds of flour.
Okay, right.
It's
Science.
science. It's fine. Oh man. So do you have any particular experiences of teachers who've tried this in their colleges or in their classrooms? Have you gotten any feedback?
Yeah, the school that comes to mind is a two-year community college. I don't know whether our audience includes that level or whether it's different levels than
I think
that.
we're all over the place, but yeah.
Yeah,
Variety. Yep.
College of San Mateo down near San Francisco. Daryl Sanford and some of the other people down there have set telescopes up and have the students doing most of the examples that we've done here.
Cool.
And again, it's not something you can throw 30 students at simultaneously because there's only so many telescopes available. They have smaller telescopes, but what they found is the students really like it because they're actually doing some of the things that they've been hearing about in their lectures. That hands-on experience. I mean, gas tubes are fun, but stars are more fun, I think, is what it turns out to be.
And quasars are even more fun. You don't get more fun than quasars.
Yeah, but at the other end of this, other end, I mean, the community college level, in my opinion, is the sweet spot for these kinds of activities. You can do them, and I'll tell you an example in a moment of a much younger group. But it seems like, again, you all are in the education world as well as the audience, but my impression is I'm not an educator by trade. Among other things, just to compliment the audience, I'm blown away by how hard teachers work. And I had no idea until I started talking with teachers. That teachers are routinely working till 8, 9 at night or later, grading papers. They don't have time to mess around. They're busy. They're really good teachers. But this was the school I mentioned over near here in Redmond, near Microsoft. And what they did was it was an 8th grade color and light class. And this particular teacher had the students, I mean, it was total bedlam, but it worked. I'm accustomed to a much more maybe 30 or 40 year ago lab that was much more controlled and disciplined. This was pretty much just throw the kids at it and let them do it. And the amazing thing is it worked. And the kids were looking, and we have an example of this on our website in a video, YouTube video. They first looked at a lemon with our classroom spectrometer, and they saw a nice yellow peak right around yellow.
Okay.
Then the students took a snapshot, that dates me, a photograph of the lemon on their cell phones. And what student doesn't want to pull their cell phone out in class and take a picture? Then they pointed the spectrometer at the cell phone, and again, computer screens just have red, green, and blue.
Yeah.
So there's no peak in the yellow. There's 2 other peaks. I can't remember what they are. Red and blue, maybe. Red and green.
I don't remember.
There's 2 other peaks that are combining to trick the eye into seeing the average of yellow. And for students to see that, and again, it's a hands-on and it's computer screens. So that was a really exciting activity for the kids. And it was tied in. He tied it into his light and color curriculum. So the classes before, he was teaching some of the common subjects that some of our audience may have been. How shadows work, this is really elementary things. And then to do the lemon was really the pièce de résistance, I think is the term.
Yeah.
So whether it's kids at that age or whether, again, high school students, the quasar images are done by all sorts of high school teachers. That's easy. What I'm seeing in high school is that the teachers don't have that much time. There's just so much to cover, as you all know, with this, especially with the new standards. New standards are emphasizing light, color, electromagnetic spectrum, so this does tie into the new standards well, and can basically dovetail in a lot of different ways there. But to demonstrate the spectra with this, sometimes is all the teachers have time to do. They may not have time. I mean, it's pretty disruptive, I think, to a teacher to try and totally bring in a new lab. Just drop it into their class. It's a risk, and it takes a fair amount of work. And so what we're finding is a lot of instructors will say, I'm going to use this as a teaching aid, and if that works out and I'm comfortable with it, then next year maybe I'll get some more cameras and actually have the students do a little bit of hands-on.
Yeah, I was going to say that's actually a nice way to introduce things. A lot of teachers I know is, they're not ready to invest, and they don't know if they should invest in a huge big thing, in one leap. So give me a piece of it, give me one activity or one part, and I'll try it. And again, like we talked before, I'll get comfortable with that, and then we'll expand it as I feel comfortable doing that, and as I can maybe build an activity around it, and then maybe the next year I add another activity to that. And it just kind of goes from there. So it's a great way to start.
But we do know some teachers who are fortunate to be able to teach a whole semester or even a whole year just on astronomy. And I think in high school, and those teachers could really use this as a lab and bring it in. And I'm thinking of this because I just saw the high school kids in town at my public night last night. Teachers who have an astronomy class could bring this in as a lab.
Yeah, as you mentioned earlier, Nicole, so much of, they say 80%, I don't know how they measure that, somebody counted a lot of pages, 80% of the astrophysics research is done with spectroscopy.
Wow.
Visual light or other wavelengths, I suppose. But so it's such an intrinsic, it's such a core principle for students to understand. How do we determine the temperature of stars? How do we determine, what phase or what period of their life cycle they're in? All of those things. And I think that for the student to be able to do that, really, the image I have is, and actually I've got it right here. It's not on a slide, and I'm not sure. Oh, there we go.
There we go.
This
I mean,
yeah, log.
This is the one graph is a hydrogen gas tube, and the other is Vega. For a student to go, or a star. And so this is where the student is showing that I've now identified, hydrogen in the classroom, and I've identified it on a star using the same technique. Yeah. For me, in my mind, I picture a student going home and showing their parents a sheet of paper. I'm doing astrophysics.
Yeah, this is my data.
yeah, and see this peak? And so it's not hard to do, and it really, to me, it's the core of the entire massive edifice of research that we've done as humanity. The shoulders upon which we're standing of giants are all based on many times on spectroscopy. So it's a core concept. There just hasn't been an easy way to teach it. So the teachers who are teaching astronomy, this is a home run. They typically already have a telescope, and so it's just a matter of the grading and software.
Tom, are you listening? Not you, the other one, the one that teaches high school. I'm going to show him this episode.
And just again, one of the things, because I'm such an evangelist for this, is I'm really passionate about seeing educators do this kind of thing. So I guess the website is on the bottom third, or is somewhere. You'll find a lot on the website. You'll see interviews with me. I'm a contributing editor at Sky and Telescope, and I love answering questions. I mean, to me, any way that I can help bootstrap somebody into doing this brings me a tremendous amount of pleasure. It's, as you all know, you all teach and help people in your own jobs.
So it's rspec-astro.com. I put the link on the event page comments, and I will add it to the description on YouTube as well. So. Good.
Great. Well, don't hesitate. There's a contact form there, and we can Skype and talk. There aren't any complexities to this. It's a secret, I think. I think you astronomers have been keeping from us how easy this is to do. You're trying to protect your profession from interlopers.
Yep, that's what it's all about. We were jealously. Actually, I mean, I didn't actually do. I think it was my first year of grad school. It was the first time I took spectra with a telescope. I think it was the 40-inch telescope. And we had to take spectra of different stars and do the observations and classify them. But that was the first time. I was already in grad school for that.
Amazing.
Wow. We just didn't have it available to us before then. So this is really great that this system makes it available. You don't need a 40-inch research-grade telescope to do it. So that's great. Awesome. Well, thank you so much, Tom. I am going to, we're close to the hour, so I'm going to do our usual end of episode wrap-up, and then I will leave it, if you have any last message about this for the end. Today is Wednesday, which means Friday is the weekly Space Hangout. with Fraser Cain and a group of astronomy journalists and interested people who pretend to be journalists like me, who talk about the top news in space and astronomy. That is at noon Pacific on Google Plus using Hangouts on air. Sunday night Sunday night is the virtual star party, and Sunday is also daylight savings changeover in the U.S. So you're gonna have to TBA on that, unless Tom Nathan wants to throw a comment in the Q&A app, because he's one of our astronomers for the virtual star party. The last one was at 7 p.m. Pacific, so maybe they're gonna inch it up to 8 p.m. I'm not sure. But the virtual star party will be at some time on Sunday night. Check your local listings. Of course, Sunday night is the premiere of Cosmos. So, you may have to make a choice. Do you want to see the virtual
happening?
There's too much astronomy happening on Sunday night. There'll be the virtual star party in Google Hangouts, and Cosmos will be on TV. So, have fun choosing between those. Monday at noon Pacific is the live recording of Astronomy Cast, assuming that our beloved leader, Pamela Gay, is not too sick. Please get better, Pamela. I'm afraid to go to her house. Everyone's sick there. But unless otherwise noted, they should still be doing Astronomy Cast on Monday. And then that brings us back around to Wednesday. And next week, do you have the schedule up? I'm really bad at this.
No, I'm sorry, I don't. I should remember to do that too.
Next week's Learning Space. I'm like, I could do this. I could do this. It's right there. I was just editing the page
a while ago, and it's gone.
I was just editing the gosh darn page. Also on the Educator Zone blog, if you go to cosmoquest.org and click on Educate and Educator Zone, we just put up a guest post from Jessica Krim, who you may remember from 2 weeks ago. She did the cupcake geology lesson, and she wrote a little bit about that and posted we posted the link to the PDF on how to do cupcake core samples. Next week we are talking about the NASA wavelength. So I actually just got an email from Morgan Warner at NASA to talk about the motherlode of NASA educational materials and how you can use that to find what lessons and activities you need for your classroom. It's a really spectacular system, so we'll be digging into that next week. So yay! All right, so that's our upcoming lineup of shows.
Woo!
8 p.m. for the virtual star party, says Tom Nathy. So that is 8 p.m. Pacific. It's getting later, guys. Get yelled at. Tom also says, the quote given to me, a photograph may be worth 1,000 words, but a spectrograph is worth 1,000 pictures.
All right.
How do you like that?
Good way to end up.
Do you have any last thoughts for us, Tom? Go check out his website, check out the contact form.
Nope, nothing really last. Thanks for the questions. Tom, I'm in the Pacific Northwest, too. I've been down and met David down there in Portland and presented at the OMSI Star conference that they have every spring a couple years ago. But no, like I said, I'm here to answer any questions from our website, and this is an easy, really exciting activity that can add a lot of opportunities to your students. So go for it. That's all I got to say.
Excellent. Well, thank you so much for being on the show, and thank you everyone for watching. We'll see you next week.
Everybody. All right.
We have everyone back. Okay.
Back.
Good.
Yay! Hey, it's always good when things work. All right, hello.
Up a very small grating that screwed into my telescope, and was just really astonished by the science that I could do. And so I ended up writing a piece of software. My day job pays the bills, but the software is where the fun is. And basically, what I enjoy is introducing, whether it's educators or amateurs, to the possibilities that with very little equipment. I mean, I think most of us think we need to have PhDs like most of you, as well as big telescopes like many of you, I suppose,
Right.
to do spectroscopy and actually discover, science, and discover that we can observe physical properties of stars at a distance. So that's how I got involved in this, and it's been very exciting to be. I feel like I'm an ambassador or an evangelist for amateur or low resolution, inexpensive spectroscopy.
So spectroscopy is incredibly important to all of astronomy because light is still the way in which we get most of our information about the cosmos, and breaking down the light and seeing what it's made of. So this system. So when you say low resolution, what does that mean? Low resolution, low spatial resolution, low spectral resolution.
Yeah, low spectral. I mean, amateurs can get very high-end equipment, but with a simple grating like this, and this is just an 1.25" grating that sells for less than a couple $100. Just screwing it onto any old camera. And we could talk about classroom lab tools, but this one is really where we do the astronomy.
Yeah.
We can get down to, and again, amateurs talk in angstroms, and we're talking, 30 angstrom resolution. So you can see all sorts of features. Again, just a review for people who aren't familiar with it, of course, what we're looking at are the absorption, for example, of the gases around a star that's basically cutting out certain portions of the spectrum. So we see gaps in the otherwise Roy G. Biv continuous spectrum. And we can actually observe at a distance, the composition and other physical properties of stars, as you all know.
I can show the very detailed, I think, is that a Nichelle spectrum?
Yeah, it is, and that's the sun.
Yeah,
and you can see those gaps, and each of those gaps, of course, is related to a particular electron jump in the actual atmosphere of the sun. And in fact, I think the next
everyone, welcome to this week's Learning Space. My name is Nicole Gugliucci. I am a postdoc with CosmoQuest. I have with me my co-host here, Georgia Bracey.
Hi, everybody.
We're literally through this wall.
No, so close. Yes.
So close, so close. Oh, we're neighbors. And I also have Tom Field, who's going to be talking to us about spectroscopy.
Hello.
Hi, Tom.
Good to see you.
Welcome. So we have a couple of things to go over. First of all, if you would like to say hello and ask a question and chat with us, which Guido's already asking which one to use. We prefer the Q&A app, so I see Guido says hi on the Q&A app, Nancy says hi on the Q&A app. Hello, everyone. I know some people still prefer the event pages, either the normal one or the video one. I will try and keep up with those as well, but the Q&A app is the best bet. And I'll try and watch the YouTube comments as well. So feel free to join in, use the Q&A app, say hello, +1 to each other's comments, and do all that fun stuff. So we want this to be interactive. We also have a hi from Tom. Yay, hi. Awesome. Okay, so I do not have a hands-on demo to show today because I'm still in post-science online stuff. I was gone last week. Georgia hosted the show, and I bumped in 20 minutes late. So thank you.
You were there.
I was there. So I still need to go back and catch the beginning of that show because it seems like it was a really good conversation. So that is all good stuff. So I don't have a demo but we are going to be talking about some interesting stuff you can do in the classroom or with groups. And so Tom, tell us a little bit about. So I'm going to share the link. While you tell us a little bit about RSpec Astro, your introduction to real-time spectroscopy.
Yeah, I was an amateur astronomer for years, and I wanted to do a little science. I think we all have inner scientists in us that are looking to get out. You actually have outer scientists, but whether it's a teacher who isn't specializing in astronomy or an amateur, or we all want to do some science, and there just didn't seem to be much that was being done except imaging. And so I picked, let's see, where are you in the slide deck?
That's number 1.
Oh, yeah, just go one more slide.
Okay.
We can zoom in a little bit. Yeah. There we can see, again, just certain gaps. In one more slide, we can actually see them named, where we can see that, again, the absorption that's due to transitions of electrons in the shells or in the shell of the sun of magnesium are creating those particular absorption features on the bottom, or on the top, excuse me. So to be able to see these and observe them in a telescope makes it real. Otherwise, it's just a, paper theoretical experience that students and amateurs are getting. And so with this grading, really, if you just use it visually, you see a little rainbow, but you can't really see the gaps in the spectrum. Right. For that, you need software that actually blows it up and then graphs it. And that's what I ended up doing, was writing a piece of software to do that so that we can do it real time under the stars, with video even. And, I'll set a telescope up in a high school parking lot, like a 6-inch telescope and a video camera, and show people the absorption features on, for example, Vega, a bright star, for example. And it's amazing what we can see. I'm just looking for an example in our slide deck here. Try slide 56. See if that shows.
That is showing the Wolf-Rayet star.
56 is? Wrong. I've got my numbering wrong. That's the Wolf-Rayet? Oh. Okay, well, let's look at that. That's a good one. That's fine.
Yeah. Oh, wow.
So this is, look at, and go one more slide ahead if you would.
Oh, okay, here we go.
So at the bottom we can see the rainbow. And you can see Janet here in the UK with just a 30-second exposure and a DSLR and a grating. So in terms of hardware, all she had to do was pick up a grating. She's seeing very, very bright features on this star, emission lines. Now, frankly, you all know a lot more about these particular types of stars than I do. I had to go to Wikipedia and read up on Wolf-Rayet stars.
Right.
But, these are stars where, as I understand it, and you, I hope, will correct me when I get it wrong, the outer shell of these late-stage stars has been